Summarizing what I said in the first several minutes. The Stokes theorem and the divergence theorem, it comes down to understanding that two different integrals are the same and understanding what those integrals are and what they represent. If you understand all that, then it's easy to remember why you're doing what you're doing, and you're more likely to be successful. Of course, you got to be able to do the integrals. That's one bottom line. So what do? You integrate f dot ds over a path. Okay. Stokes theorem, or del dot f dot b big S. For now, you got little s here, that's path. A big S is an area increment. If it's a vector, ds, d big S, it means the vector with magnitude ds normal to the surface. Okay. And n would be uniform in this case, ds would be okay. And you know this n ds becomes your tu cross tv. It's normal. This magnitude is equal to the area of the increment. Okay. Divergence there. You got the divergence, which is del dot f over the volume. Okay. And del dot f, we talked about it. Now we'll talk about it. At a point, if you take a volume and shrink it around that point, if you always get non-zero ratio of the flux through that surface, flux of that through that surface, ratio of that flux to the volume, then you got a non-zero divergence. That'll happen because the del dot f is zero at that point. Okay. Now on the bigger volume, you integrate the whole blamed del dot f at every point. Okay. It's like a partitioning the volume. Each little increment. There's a volume increment that you go multiply by the del dot f at some sample point within the increment. And that's kind of dovetails with what I just said. And then your integral is going to represent total inflow or outflow, total flux through the whole surface. And then you do total flux through every little increment, it adds up to the total flux through the surface. The same as with Green's theorem. Okay, you got little rectangles, break your region up into little rectangles, and all the rectangles in the interior. The path integral cancels out. Because every rectangle in the interior borders another one on each side, where the integrals going in the opposite direction. Okay, well, we did that pretty extensively. Make sure you've got that picture. With the divergence here, it's just the same, except with the volume. You can see if you have a million little volume increments, okay, and you always have a flux out of each one, then by the time you get out here to the total boundary, you've got a whole bunch of flux. Okay. Can't really have that with the idea. And basically the del dot f over tiny volume just tells you how much flux there is out of that volume. You add it all up. Total flux through the surface. I don't repeat myself. Almost perfect. Okay. Well, I understand that. Because almost every field of engineering or applications, especially. Civil, mechanical, okay, chemical. We want to talk about more about how to set up intervals. I think we have less problems setting up volume intervals and path intervals. When we do surface intervals, we have that weird parameterization. Got to parameterize the surface together. I mean, there's been some shakiness over parameterizing paths down for complicated surfaces or partitioning the surface. So for describing the surface in terms of inequality. But I think we're getting there on both of those things. And probably making some progress with surface layer. Most people did fairly well, real well on homework. As long as that homework is done the right way, you should know how to do it all right, okay? But you might need more practice. All right, well, let's just get into some nuts and bolts. We talk about the flux of the little triangular region in three-dimensional space. I don't remember for sure what the dimensions were, but I think we have 6 along the x-axis, maybe 4 along the y-axis, or maybe 1 along the z-axis. I think it might even be what we have. That'll be 3. Okay, forwards as well as 3. And we have some function. Surface is just problem. Okay, the path is set up as C1, C2, and C3. And I suggest you think about what I told you about different ways you can parameterize that path. Okay, many ways it can be parameterized. Let T go from 0 to 1. It is pretty convenient once you get the paths set up, because you can kind of do it all in one. If you're careful, you want to write out all 3 and see that the same limit. If you have the same limits on T. If you have different limits, well, you have 3 intervals, and no matter which, that interval turns out to be. Okay. So the surface is x plus 3y plus z equals 12. We could derive that. We could take a vector along this side, a vector along this side, calculate the cross product to get the normal vector. Of course, we understand planes, we know the normal vector is going to be 2i plus 3j plus k. We know that if x and y are 0, z equals 12, so we have this point, and so forth. We know all that. Let me use back at the moment. It's 2i plus 3j plus k. in the unit normal. Is this, and I guess I'm probably using the same numbers I did before. I didn't remember if the 3 went here or here. I remember having a square root of 14. And if this was a 4. Not what we have. Okay. There's your normal vector. Now we have to have a vector field. Use any vector field. Okay, I'm gonna let F equal X I plus ZJ plus YK. Maybe I'm not. It's nostalgic, hearing those sounds. That's the way news sounded when I was a kid. Okay. And actually, news is fairly objective back in those days. That's a huge loss, but it is back now. Okay. Now, what we want to integrate is we want to integrate del cross out. If we want to do this. If we set that up, I better do it. It's funny. Don't trust my brain today. Okay, it's going to be I times 0. It's going to be J times 0. It's going to be K times 0. So I don't like my variables. I'll put a Z here. And that's there. So I have to get something. Okay. So again, I partial y with respect to y is 1. Partial of x with respect to z is 0. I'm going to get on. Okay, I'm going to get 0 there, and I'm going to get 1 there. I plus j. And then with k, I'm going to get 1. Okay. Now that doesn't have any extra y's in it. So I'm going to change it a little bit. And I'm going to make this z squared. So that when I do my j, I'm going to get the partial of z squared. So I'm going to have a z there. Now this could get very complicated. Try to do a simple example here so we don't get too hung up on the integration. We want to see the process. Okay, Stokes' theorem says about this situation. Integral over boundary, which I'll call C1 plus C2 plus C3. F dot ds is the integral over the surface, and I think they use D for region. Almost any letter used has its disadvantages. Of del F cross N, del cross F dot N ds. We've brought pictures of how that works. You divide this F region up into little rectangles with a curl. Represents the circulation within each of them. Okay. This integral is tedious. But easy. So we can easily do it. Okay. This integral turns out that function is pretty easy. If we just set up parameterization, we should be able to do this one. We don't want to take all the time to do this. We'll go ahead and put up with a little bit of pain. And it's not very painful. Matter of fact, you can actually shortcut it. Because we have the same normal every region. And well, we'll see how that would work. Let's go ahead and go through the parameterization process. Now, if we parameterize the surface, we left R of P. Now, I didn't use the R of P notation. It's good notation. We've used it a lot. I just haven't used it with parameterizations of surface. Okay. But it's good to write this out formally. Your R of T is just going to be xi plus yj plus zk, right? Z is 12 minus 2x minus 3y. Okay. Because we don't want a third parameter. We can only use two parameters. Why does this? Everything I've said has been in front of a camera that zoomed back to the moon or something. Very irritating. Okay. Anybody that's watched this video from the beginning, well, nobody in the right mind would. It's with the way it was zoomed. Much less the way I'm explaining it. Okay. So anyhow, there it is. There's a whole board of apologies that we've gotten as far as video. It might be because it's got a big enough screen to probably read things. You know, we've got a technology request. I think I'm going to replace the camera that actually allows me to set. Zoom. Automatically small. Okay, great camera. Okay, anyhow, we got xi plus yj plus zk. We have to have just two parameters. We can't use three parameters because it's only a double integral among anything. Think about that. And this would then be 12 minus, I think I got the right numbers, 2x minus 3y Okay. It'd be a little hard to read that. But now that we're zoomed in, maybe. Okay. Okay, so, RFD. Here's our normal vector. Here's our delta cross out. So. Integral. Or DS. We got a couple minutes. Because this is a unit normal. Our DS is going to be a dydx. Okay. Over this region here. So we're going to be integrating from 0 to 6 with respect to x, and from 0 to 4 minus 2/3 x on what? Okay, check that out. Is that clearly? If x equals 6, then the limits of y are just from 0 to 0, because right here at the tip of this triangle. Okay, well, 4 minus 2/3 of 6 is 0. Okay, and it's got to be 6 here, and it's got to be 4 here when x is 0. If x is 0, we get it. So we can kind of do this by inspection, but you can also just graph it, see what the y-intercept is, see what the slope is. Y-intercept is 4, the slope is negative 2/3. Okay, so whichever way you get it, by hook or by crook, it's easy to describe this region. There's our parameter space. Now, our parameter is not the real surface. Okay. So how big is an increment of this surface? 2 ways to see it. Yeah, I said something wrong before, so let me go back to this. Your N DS is what it is. Okay. When I wrote down N here, I said something about this being a unit normal. That contradicted what I said about the NDS being your area, your vector area increment. Got to be normal, and it's got to have right bottom or the right area. Okay. So your normal vector is not a unit vector. Whereas this. What this tells us is the magnitude of this vector is the square root of 14, which is a little less than 4. The area of this thing a little less than, or a little less than 4 times the area of this triangle down here. How steep is it? That's got a slope of 2 here. It's got a slope of 3 here. But it makes sense you'd have some multiple of this, it might be closer to 4. Well, if we do our TU cross TV. Here we go. Okay. Let's calculate. TU, but it's actually TX because X is not a parameter. But if this was U and V, and I did that last time, we'll let this be U, this be V, and so forth. But unit tangent TX, and I actually calculated it with U and V. So if you look back at what we did last time, there it is. If you review what we did last time, it's familiar to you. Okay, TX is just I minus 2K. Ty equals J minus 3K. Tx cross Ty, and again, we did this with U and V, and it was X and Y this time. I cross J is K. I cross K, make sure I cross K is negative J. It's negative 3, so it's going to be 3J. Now let's get 3J here. And then J cross K is I, so we're going to get minus 2I. Okay. Normal with that because that isn't normal for that surface. What am I doing? Well, we're going to go with it has the same magnitude. But if this is the equation, then I would make it on the 2. I can spend time puzzling on it, but it's going to do this. But one of these is wrong. And they should match. TX cross. Whoa. It's TX cross Ty. K cross J, not J cross K. So that's treating the cross product as if it was something. You know, okay, so. Just reiterate, there's our del cross F. I'll write it down here again. Then I'm going to find a way to give myself more room to get it all written in there. Del cross F is your I plus 2J plus I plus CJ. So plugging this in, it's a dy dx. I'll try to write it. The room I like myself. Okay. It's there's my dy dx out there. It's going to be hard to read. So now I'm going to get the double integral over these regions. I'm not going to finish the end. But I dot 2I is 2 plus 3z. I'm going to need more room because z is 12 minus 2x minus 3y, right? So if we get to this point, as I just did. I should really have substituted for Z before I wrote this down. Really should have substituted for Z there. Switch, but it's not too late. You see, I don't have a Z in here. I can't integrate Z. And Z is not a constant. On the surface, Z varies from 0 to 12 and varies waves. Okay. This is a double integral of, well, it's going to be 2 plus this, which is going to be 14 minus 2x minus 3y. Y dx. Now, at this point, I stopped writing the limits and integral. So what they are, and I have to write pretty small down here. And if I say, I'm not gonna finish it, you can finish it. If I have it on 30 seconds flat. Maybe 3 minutes if you're slow. Okay. Maybe longer than that if you're really slow. But still try to speed up before you get to the exams and you're not in long. Okay. Okay, there's simple linear. If we integrate y with respect to y, then plug it in for x and so forth. So we integrate. Oh, I think I got my integral backwards. No, when you integrate with y, we'll fill it. So, okay. That's the process. I could have used this normal as well as this one, but this shows you a little bit more about that. Du cross T thing. Hopefully you picked that up well when you did the surface area. Okay. The next thing we looked at, and I remember what it was, so it's very simple. It turns out to be a paraboloid of revolution. Or this. Okay, you got this open paraboloid of revolution. I don't remember what the function was on that point. It doesn't really matter. Well, yeah, it actually does kind of matter because some functions are easier to integrate over the boundary than to integrate. Over the surface. This is like y equals z squared rotated around here. Now I'm going to parameterize it. I'm just going to do the parameterization. If I project this back on the xz plane, I find that I can parameterize this if x equals. And I think we got this one. Okay. This is a circle of radius 2 in the xz plane. Puts a little path for that, just scale. Okay. Then Why is it what? Oh, I'm gonna be z squared, at least from this line. But it's really in any circle. It's gonna be this. The trying to find the words we don't want to draw a picture. Y is going to equal u squared. Okay. So there's any little circle in there. Well, if you do this in the YZ plane, then Y is going to equal Z squared, right? And Z is just the radius of this little circle, which is u. So I think that's okay. Your surface interval of LF cross M ds. Your M ds is basically just your TU cross TD. With a DU dV. Okay. That's all I'm going to do the page. So you can kind of get used to that. You can memorize it if you want to. Once I ask you to explain it, you'll be okay. Okay. It's this times dotted with, sorry. Dotted with this and then du dv. And u and v have constant limits. So it's limit of v that is nothing u and okay. But of course, this is equal to the integral over the curve of f dot dx. Well, we parameterize the curve here. It's just a circle of radius 2. Here I got y equals z squared. So that does what I'm thinking, that it's equals y squared. Y is just square root of z. Wait, no. 4. We're gonna probably look at another question, which is officially from there. Yeah, that has to be. Don't even think about what I might have been looking at. Okay. Way too obvious. It's anyhow, this is circle then. Of radius 2. In the plane, y equals 4. So C so to parameterize this. So you have an R of T for this. You have an R of T for this. I don't recall noticing what did about that notation. Anybody remember? So kind of keep it consistent with the book. Okay. Actually, what I think is. Book is using T instead of R for the surface. That's where we get the T, the TV, right? Let me go back. Yeah, that's it. I think that's the only place that we would use that. But that's like your R of T vector for the surface. Got two parameters. So we do TX and TY, you're actually not doing RX and RY. Okay. So excuse the notation, but all of these. So, okay, so. And it's not. Not T. T, there's no T over there, is there? How many times did I say you need two parameters to describe this, and then I wrote it as if it's one parameter? T of I held myself back a little bit. You didn't hear a sonic boom, did you? I become a unit because it costs us. Okay, well. After that, okay. So now everything I wrote over here is more consistent. I'll try to use the same representation. Okay, so R of T for that circle, without comment, I'm just going to write it down, is V cosine T of I plus 2 sine T of K plus two J. In other words, X is cosine of 2 cosine of T, Y is 2 sine of T, giving a circle, and say X is 2 cosine of T, Z is 2 sine of T, giving you a circle parallel to the YZ plane. You're in the plane where Y equals 4. So you ought to have a 4 in front of J. What that's going to explain that. Put my arrow. Okay, there's your RT. Now, keep parameterizing circle, which is the boundary of this thing. Parameterize this boundary. Then we need to parameterize surface. Well, right here is X, Y, and Z. So your T vector you not open. Be careful. Because we're kind of in a habit of X being the cosine of B, Y being the sine of B, but it's Z now that's use. Okay. So to avoid those little pitfalls, I just barely do. And it's going to be easy do TU cross TB. Okay. And I was gonna say there's no U dependence in the Y direction, there's no V dependence in the Y direction. It's gonna be 2U J plus 9V times. Then PV is equal to negative U sine VI plus U cosine VK. There's no J dependence because J depends on U. Yeah. I would just write it out. Now, the other part of the parameter, well, I've got this part of the parameter. So that. See if I can actually write it down. There's okay, the integral. F dot ds becomes the integral from, I don't think I wrote my limits on T. But anyhow, so yeah, it's a circle. These are going to go from 0 to 2π. And there's no T dependence in J. Okay, so it's the integral from 0 to 2π. Oh, F, whatever F happens to be. Okay, I'm not going to put it in there. We're just going to do it generally. Let F be PI plus QJ plus R, equal P, Q, and R functions of X, Y, and Z. That we substitute this from relation. Okay. In other words, X is going to be 2 cosine T, Y is going to be 4, T is going to be 2 sine T. Then this is going to be dot R ds. What's our ds? Well, it's actually the R we want to do this. Okay. Put it in here. Okay, this is the same as saying, right? So here's our parameterization in terms of T of our half. Our ds is then dxi plus dyj plus dzk. Or just the derivative of that. So I'm going to do it as VR, and that's going to be the integral from 0 to 2π of PI plus QJ Was hard to make. Dot. Did it a minute ago, didn't I? Anyway, it's gonna be. Negative 2 sine phi plus 2 cosine phi j. dt. Now, that's all pretty straightforward. And as long as your P, Q, and R are two weird. P's got an R tangent of the natural log of T. You're probably in trouble. You're probably in trouble with this integral too. And that's going to be difficult to integrate, but there are other things that look like they ought to be simple, but they're hard to integrate. And you see those when you do something problem. Okay. So that's this interval. And of course, now we can write that as negative 2p sine p and all that stuff. We do that dot product. That all just falls out. Once we have the parameterizations, everything pretty much just falls out. Okay, so the integral then of okay, now have I done L cross F? Well, I haven't because you don't have an F. Okay, it's going to be like py minus p. Py minus pz r. Okay. Anyway, it's the cross partials with the IJ. And we could write that out with the cross partial, but it's easier to speak with this one. Okay. And then it's that dotted with TU cross TD. What are your limits? Well, U goes from 0 to 2. D goes from 0 to 2 pi. This would be a rectangular region in UV space. This is what you multiply by that rectangular region to get the area multiplier, if you wish. Okay. The magnitude of this times the UGV gives you the area corresponding to your region in your parameter space. Okay. It transforms your parameter space into a normal vector with a magnitude, the appropriate magnitude to multiply the area in UV space. Okay. Well, then everything we've done here allows us to easily write that integral. And the TU cross TB, not doing the right, etc. We do that much, we're done. And we see that if we do a few of these, everything's pretty straightforward as long as one of silly little mistakes. Okay, you see me make all the time. Write it out carefully. The trick is getting a good parameterization. Keep everything with Stokes theorem. Okay, got to parameterize the curve. You got to parameterize the surface, and then you look at both integrals and say, geez, which one am I going to do? You do the one that's easier. and then you have the other. Now, if you're trying to verify space there, which is important to do, you do them both and see if they come out the same, and if they don't, you go back and fix it. Fair enough. Okay. Now, what about the divergence theorem? Okay, let this be the same region we just did. Okay, it's a closed region. We could. So we have a surface. Closed region can be described by um, put that down. Y goes from z squared up to 4. And it's not just z squared, it's x squared. Plus z squared. Okay. Now that should be pretty straightforward. We've done volume intervals. It look pretty straightforward. Certain about that. Well, take it through. Go back and review. Integration on it. So there we have it. And of course, we could do this in full. So, well, we'll just stick with the right thing. Okay, so we got this closed region. The surface. I think they use the surface. They want to use capital S. For the, want to make sure I get this. Yeah. Okay. Just double check. Okay. So there's your D1. We've already got that. That's the curve file. D2. I'll just describe it by x of x, z. It works. but that's too small. But it's just, if you got X and Z, and then how far do you go out? You get to the surface, and actually. I'm describing the surface, but. Decompose with that. Every 4J. Plus ZK with the appropriate limits on X and Z. So let's say. S going from negative to Y going from 4 minus X squared plus X squared. And the negative square root of 4 minus X squared plus square root of 4 minus X squared. Okay. So again, that describes the region, Y component of your S vector is always 4. So you're always in the Y plus 4 plane. And then you've just got a circle of radius 2 parameterized in the XZ plane. And again, the parameterization or the inequalities for circular region or an elliptical region should be straightforward. If not, go back and do it. Okay. With more exercises on that. There's plenty. Okay. So now the Hurwitz theorem. Triple integral of del dot F dV equals surface integral of F dot M dS. And why is it F dot M? Okay, and we've talked about it. If you got a surface in this direction and a vector field in this direction. Okay, so you've got increment in this surface, okay? And well, with the surface like this, okay, you got maybe the surface increment here is about this angle. And it's normally outward like this, okay? And if you do F dot M, you want the flux into or out of the region, and well, if F is in this direction, and the normal vector is in this direction, you do the dot product of that within, you get the component of that parallel to M. And if you don't understand that F dot N well, I said there ain't quite right, I gotta qualify it. If N is the unit vector, then F dot N is going to be the component of F in the direction of N. Okay, if N isn't a unit vector, then F dot N is going to be whatever the magnitude of N is times that. And that's a statement you should totally understand from earlier chapters. You might have to review a little bit. No, it doesn't mean you can't calculate it, but you really need to understand it if you're going to understand what this is telling you. Okay. It's for that reason that you got the flux. It's a component of F. It's crossing the surface. We'll probably talk more about that next week. But we've already talked about it in the previous chapter. Okay. Well, that interval we've been looking. Set up whatever F is. The interval is going to go from 0 to what? -2 to 2. Vector X. And it's not negative square root of 4 minus x squared to 4 minus x squared. Because I'm doing the wrong intervals, I'm trying to do this. And look at that. Over here, okay. Again, looking at this, x goes from 0 to 2. Then, z goes from 0 to the square root of 4 minus x squared. And y goes from, very carefully, x squared plus z squared plus 4. Okay. Oh. Your del dot F, whatever your method is. You can do your del dot F. If it's, and I really can easily do it. And that's got to equal then the integral of F dot N over your ds, which will be pretty much identical. Except that you have an F dot M instead of a del dot F. The U dV, let's see which one's U, which one's V. U goes from I use T here. I think I use U out here. I'm going to change that representation. We can simply what we did before. Okay, and now U goes from 0 to 2. V goes from 0 to 2 on. And of course, N is your TU. Plus PV from before, so that goes here. Now you've got your integral, and these two integrals should come out the same. Okay. Now that's kind of a short description of the divergence there, but that's really what it comes down to. Being able to set up and do those integrals and understand what integrals are equal to what. And then especially understand the geometry, and we'll talk more about that too. So that should have you set up well enough to do all the problems I see. Okay. And, turns out you need a little extra time on the problems. I could give it to you. Actually, even more important, Tuesday than the divergence theorem is the chapter review. Because that helps you pull the Stokes theorem, the divergence theorem, these integrals and everything together. Okay.